Solving the DePIN utility Trilemma explained by Raymond Clough. DePIN, which stands for Decentralized Physical Infrastructure Networks, represents a novel approach to providing essential services like cloud storage or computing power. Instead of relying on a single large corporation, such as Amazon or Google, DePIN leverages a global network of individual people who lend their computing resources. These individuals are compensated for their contribution in cryptocurrency tokens. The core challenge facing DePIN projects, referred to as the Trilemma, is the attempt to simultaneously achieve three mutually incompatible goals. The argument is that for enterprise-level adoption, a project can typically only succeed at two out of the three. 1. Stable prices, budgetable. Real-world businesses operate on strict budgets and require predictable costs. Stable prices ensure that a service's cost remains roughly consistent month to month, for example, $500. If a service's cost is tied directly to a volatile cryptocurrency, a company's bill could swing from $500 to $2,000 unexpectedly, making the service unusable for financial planning. 2. Free-floating token value. This goal is critical for attracting early investment and funding project growth. It means the cryptocurrency token's price is determined by the open market, driven by traders and speculation. Investors are drawn in by the hope that the token's value will significantly increase, effectively funding the build-out of the physical network. 3. Credible decentralization. Decentralization is the fundamental value proposition of crypto. It means the network has no single boss, company, or central point of control. This is intended to prevent censorship and avoid the control exerted by large tech monopolies. The barrier to corporate adoption. The central failure point for many DePIN projects lies in the conflict between stable prices and free-floating token value. While the underlying technology, data storage, and computation often works well, the business case is flawed. Because the token value fluctuates wildly on the open market, the service's price does too. A company's chief financial officer will reject a DePIN service because they cannot budget for it. For example, a company might switch to DePIN to save money. But if the token's price suddenly doubles overnight due to speculative trading, the cheaper option instantly becomes twice as expensive as traditional services like Amazon Web Services. Conclusion: speculation kills utility. The conclusion is that as long as the project's native tokens are primarily treated as speculative assets or gambling chips, their price volatility will be too extreme for reliable, utility-driven businesses to adopt them. The hard truth for DePIN builders is that they must make a difficult choice. To achieve the necessary stable pricing for enterprise use, they may have to sacrifice either the highly speculative, get-rich-quick token model or the ideal of absolute decentralization. Is there an alternative method to solve the trilemma? Yes, here is the technical architecture. The underlying technology of the project is a modern, highly viable approach to embedded systems management. The edge cloud paradigm with Cloudflare workers. The hosting choice must be significant to handle payloads. Cloudflare Workers is a serverless platform that runs code on Cloudflare's global edge network rather than in a centralized region. For a network management system, this choice implies a serverless control plane. Low latency. Logic runs at the data center closest to the user or the router. This is ideal for a distributed fleet of routers that need to check in for configuration updates or report telemetry. Scalability. The system can theoretically handle thousands of devices without the developer needing to provision a VPS or manage a Kubernetes cluster. The mechanism. The architecture involves the OpenWRT routers, clients, making HTTPS requests to the worker server. The worker processes the request, for example, device IDX needs config Y, and returns a JSON payload. It interacts with a lightweight database like Cloudflare KV, key value storage, or D1 SQL at the edge to store device states. Python integration is the brain. The existence of a brain package on PyPI uses a Python component. While OpenWRT routers often use Lua or C for core services due to size constraints, Python is increasingly common on more powerful gateways, for example, Raspberry Pi 4 compute modules. This brain likely acts as the local intelligence unit. It bridges the gap between the low-level UBIS calls, C/Lua, and the high-level cloud logic, Python/JS. It might handle complex logic like if latency greater than 50 milliseconds, trigger BSS transition before sending a report to the cloud. The embedded core OpenWRT. The true technical value of the project lies in the modifications to the OpenWRT core, specifically host APD. The UBUS revolution for host APD. Standard host APD is controlled via a command line interface, host APD underscore CLI, or configuration files. It does not natively speak UBUS, OpenWRT's native IPC bus. By patching UBUS support directly into host APDE, the developer is creating a API-first Wi-Fi stack. This allows other programs on the router to subscribe to Wi-Fi events, for example, client X connected, or trigger actions, for example, kick client Y, using standard JSON messages over a Unix socket. This decoupling is modern and highly desirable. It moves Wi-Fi management from scripting and config parsing to event-driven architecture. It allows for the creation of reactive mesh networks where changes in the environment trigger immediate programmatic responses. The BSS Transition Challenge. The patches mentioning BSS transition indicate the project targets roaming. In standard Wi-Fi, the client device, phone/laptop, decides when to switch access points. They are often sticky, holding on to a weak signal even when a stronger one is available. 802.11 VBSS Transition Management allows the network infrastructure to suggest or force the client to roam. Implementing this correctly requires complex state management on the AP. Project likely aims to be the brain that monitors signal levels, RSSI, and orchestrates these transitions to ensure seamless coverage. Combining these elements, the full architecture of project can be inferred as a Cloudflare worker acting as the global controller and configuration authority, custom open WRT firmware running on routers, a Python-based service, Brain, or a C-based UBUS subscriber running on the router. This local service talks to the modified host APD via UBUS to enforce roaming decisions and report client stats to the cloud worker. Market analysis. The potential of the architecture within the current market landscape for network management solutions. The market for cloud-managed Wi-Fi is crowded. Prosumer/SMB such as Ubiquiti Unify, TP-Link Omada. Proprietary software but cheaper hardware. Open source can use OpenWISP, various Ansible scripts for OpenWRT. These often lack the polished cloud experience and rely on central servers rather than edge workers. There is a distinct gap for a Meraki for OpenWRT, a solution that allows anyone to flash cheap commodity hardware with OpenWRT and manage it via a modern serverless cloud interface. The use of Cloudflare workers makes this extremely cost-effective, pay per request, compared to running a heavy OpenWISP server. Embedded firmware is security critical. If the sole maintainer ceases development, users are left with routers running a custom, unpatched version of host APD. In an era of vulnerabilities like crack, frag attacks, and various buffer overflows, running unmaintained Wi-Fi drivers is unacceptable for enterprise use. The project must strive to upstream its patches. If the UBUS support for host APD is accepted into the official OpenWRT repository, the maintenance burden shifts to the community, significantly increasing the project's viability. The PYPI indicator. The presence of packages like Brain on PYPI is a double-edged sword. It indicates an attempt at modularity and distribution via standard package managers. The name Collision extends to Python, is also a famous Go library used for CLI apps like Kubernetes/kubectl, and a constraint-based reconstruction and analysis library for biology, PY. A generic Brain package is likely to be lost in the noise or confused with biological modeling tools. Operational security. The intersection of the project's architecture creates unique security risks that go beyond standard software vulnerabilities. The supply chain perception risk. Modern security is driven by reputation. An unsigned binary or a script downloading components from a domain associated will be treated with extreme suspicion. Scenario: an IT administrator sees a device on their network reaching out to the developer to download a payload. They search for and find references to arms manufacturers, games, and malware, Turla. The logical conclusion is that the device is compromised. Thus, the administrator blocks the domain and wipes the device. The project fails not because of code quality, but because of trust signaling failure. Maintenance of custom forks. The project appears to rely on a hard fork of core components. Snippet evidence. The mailing list discussions show the patches are being debated and not yet fully merged. This means the project must likely compile their own firmware or download binary blobs from the developer. Every time upstream host APD releases a security fix, the project developer must manually rebase their patches and release a new binary. History shows that solo developers rarely maintain this cadence indefinitely. This leads to a zombie project that is functional but insecure. The project is viable and promising. The architecture, Cloudflare Workers plus OpenWRT plus Ubus, represents a sophisticated, modern approach to distributed network management. It addresses real-world pain points, roaming fleet management with scalable technology.